Hey programmers, Alvin here. Right now I want to go over a Python solution for this fib problem. So we'll jump right in. Let's start by laying down our base cases, right? So our base case, like we said in the approach, was if our input number n is 0, then return 0. If our input number is 1, then return 1. So that should just be a matter of some conditionals for us. So we'll check if n is equal to 0, then just return 0. And then also if n equals 1, then return 1. So nothing too fancy. And now in the recursive case, why don't I start by just laying down the brute force. So here I can calculate my answer by returning the sum of the previous two Fibonacci numbers. So fib of n minus 1 plus fib of n minus 2. And before we even try to implement the optimal solution, let's just go ahead and run this brute force. It's probably going to time out because we already spoke about how this has a 2 to the n or an exponential runtime. Should be able to pass at least some of the examples here. And I expect, that we time out on some of the larger inputs. So it looks like on test 6, we take a little bit too long. If I look at that test case 0, 6, it looks like even once we pass it along the 35th Fibonacci number, that's too large for our exponential solution to actually deal with. So now we'll work in that memoization strategy, right? And so to implement that, in Python, I want to make sure that we are able to pass a dictionary into this recursive call, and that way all of the recursive calls share that dictionary. And I'm choosing a dictionary in Python because it's basically how Python implements like a hash map structure, because it can give me an O of 1 lookup time. So the way I typically implement this is I want my main function to have the name that's going to be tested. So I need to make a function called fib. But for my actual recursive function, maybe I'll just rename that. You can call it like fib helper. Typically what I do is just put an underscore at the front of the name. And then for our main function, we'll still take an n. But what I want to do is really just delegate to my helper function. So I'm going to just return whatever my fib helper returns. But I want to pass along to it an empty dictionary. So I'll just give it a dictionary just like this. Now that's going to be a memo. So I can take that in now. And I want to make sure that this memo is passed along to all of the recursive calls over here as well. So right when I make these recursive calls on line 13, go ahead and pass along that same old memo. Cool. So now I'm able to share this single dictionary among all of the recursive calls when I call underscore fib, right? So that's looking pretty good. And now I need to add an additional base case, right? So recall from our approach video, we said that we need to be storing information inside of our memo. In particular, we want keys of the memo to be arguments n, and we want the associated values to just be the return values. So let's go ahead and check. If n is inside of the memo as a key, so if n in memo. So if you're unfamiliar with some Python syntax, this is just checking if n is a key in a dictionary. And if it is, then return the stored value associated with that key. Nice. And what I want to do is, now I need to put data into my memo, and that should just be about modifying line 16, right? And so this is a very canned formula. We're going to see this appear many times. I just take my old return value, and I replace the return with a line that stores that value into the memo, using n, or the argument to our function, as the key. Cool. And then once I do that, I just need to complete the same old return. So I'm just going to return memo square bracket n. So I'm still doing the same return. I'm still returning the same information, the same number. But before I return, I'm now storing that result, that number, into the memo. Because the whole point is maybe later on in my recursion, I actually need to know that value, that return value for a given n. And so I have my memo checking logic, I have my memo storing logic, and I also, of course, passed along a new dictionary for my recursion. So with that change, let's go ahead and give it a shot now. I'll clear this out. Let's give it a run. We should be able to pass all of the test cases now. Yep, and there we have a nice solution for this fib problem. So I just want to go over a common misconception. So it's really important that for most of these like memoization problems we do together, you're going to notice that it's really, really easy to just modify a brute force solution with memoization after the fact, right? Because I just apply these 3 changes. That is, I add a base case to check if a key is inside of the memo. I'm sure to store information into my memo. And then, of course, we need to pass along our memo to all of our recursive calls. Something that students kind of do when they kind of first learn memoization is they write very heavy-handed logic, and they kind of write bad patterns like this. So I'll say, I don't know, memo n-1 equals like this recursive call, and they write something very similar for n-2, right? So you want to avoid, code like this, right? Instead of writing like preemptive logic where you try to memoize your child calls, right? So if I picture this as a tree, like the parent would be fib of n, and the child or the children would be fib of n-1 and fib of n-2, right? You don't want to write any memoization logic explicitly about the child calls. Instead, just write your logic for yourself. So my logic is simply about n, because I know when I just make the recursive call, it's going to be like self-service, right? Every call is going to store itself into the memo. That way I don't have to duplicate my code too much. So definitely give this problem a shot on your own. Once again, if you needed some help with this one, it's a really core pattern. We're going to utilize this memoization formula plenty of times throughout the course.